Last video we decreased the temperature all the way till absolute zero. This of course left us with the other question: how hot can it get? Heat is released as waste energy when you pump energy into a system. As the temperature increases, so does the system's energy. So asking how hot it can get really comes down to how much energy can be put into the system before it overloads. So let's do that. Once again we will be using Celsius and Kelvin because imperial units are unscientific. Once again, our starting point will be 0 degrees Celsius, or 273.15 degrees Kelvin, the melting point of ice. At 3 degrees above zero is the melting point of peanut oil. At 5 degrees is the recommended refrigerator temperature for food cooling. And at 10 degrees is the minimum temperature for most plants to grow. At 11 degrees is the average temperature during winter in Spain. And the mean surface temperature across all of the Earth is 14.9 degrees. 18 degrees is the average summer temperature in Norway, while 90 degrees is the average winter temperature in Hawaii. The highest temperature ever recorded at Antarctica was 19.8 degrees at the South Orkney Islands in 1982, and average room temperature is 21 degrees Celsius, and probably the temperature you are watching this video in. 23 degrees is the average mean temperature on Earth during the Paleocene-Eocene thermal maximum about 55.8 million years ago. The average summer temperature in France is 26 degrees, and 27 degrees is the estimated melting point of the radioactive alkali metal francium. 29 degrees go for heated indoor swimming pools for recreational swimming. And at around 30 degrees, we find one of the coldest stars we have ever discovered, CWISEP J 1935-1546. Though there is a lot of uncertainty regarding its temperature. At 31 degrees is the melting point of butter, and at 34.4 degrees lies the hottest annual mean temperature on Earth at Dalol, Ethiopia. 35 degrees is the average temperature of the warmest sea, the Red Sea. And 36.8 degrees is the average human body temperature. Within 1 degree's deviation of this is still considered healthy. The average temperature of the Sahara Desert during the day can get to 40 degrees. Long exposure to these temperatures can cause severe dehydration and cellular breakdown. The highest recorded temperature in Europe was measured at 48 degrees in Athens, Greece, July 1977. The highest temperature ever recorded in South America was 48.9 degrees in 1905 Argentina, while the record high temperature for Australia was 50.7 degrees in 1960. For Asia, the highest recorded temperature was 54 degrees in 2017 Iran, and for Africa, 55 degrees in Kabylie, Tunisia, 1931. At 56.7 degrees is the hottest naturally recorded temperature on Earth, measured at Furnace Creek in Death Valley, North America. Milk is pasteurized at 63 degrees. The boiling point of water on the top of Mount Everest is 69 degrees. This is because at high altitudes, air pressure decreases. As it decreases, there is more room for the particles to move. Hence, melting and freezing points will get lower. At 78.37 degrees is the boiling point of ethanol, or common alcohol. And 82 degrees is recommended for coffee brewing and dishwasher water. 98 degrees is the melting point of sodium, and at 100 degrees above zero, we reach the boiling point of water. Exposure to temperatures at or above this are instantly harmful to humans. At 115 degrees we reach the melting point of sulfur. An oven on low is 135 degrees approximately. Sucrose, or table sugar, caramelizes at 160 degrees. The mean surface temperature of the innermost planet Mercury is about 177 degrees, and popcorn pops at 118 degrees, which is also the recommended temperature for deep frying food. At 218 degrees is an oven on high, and at 231.9 degrees is the melting point of tin. Polonium melts at 254 degrees, and at 301 degrees the Kelvin and Fahrenheit scales intersect. Lead melts at 327 degrees, and mercury boils away at 357. And then zinc melts at 419. Sulfur evaporates at 444 degrees, and the mean surface temperature of Venus, the hottest planet of our solar system, is 465 degrees. As we pass 500 degrees, we are far above anything survived by humans ever. Even with life support suits, exposure to these temperatures is strongly disadvised. At around 525 degrees, we pass the Draper point. At this point, the infrared heat signature has become so high intensity that it shifts into visible red, meaning every metal heated above this temperature starts to glow a dim red. At 639.4 degrees is the melting point of plutonium. Aluminium melts at 660 and barium has a melting point of 1000 degrees Kelvin. Then, at 1115 degrees Kelvin, calcium melts. During an average forest fire, temperatures can soar to 1170 degrees Kelvin. At about 1200 degrees Kelvin lies the average temperature of T-class brown dwarfs. At 1235 degrees, silver melts, and the average volcanic lava flow has a temperature of 1300 degrees Kelvin, while gold melts a little above that at 1337 degrees, followed by copper at 1357 and uranium at 1405 degrees. A typical basalt flow can reach temperatures around 1500 degrees Kelvin, which is also the typical surface temperature of L-class brown dwarfs. Lithium boils at 1603 degrees, while blue candle flames are around 1670 degrees, and nickel melts at 1728 degrees, as does cobalt at 1768 degrees and iron at 1811 degrees. Titanium melts at 1941 degrees, and the coolest known non-brown dwarf star in the universe is 2-mass J0523-1403 at 1917 degrees Kelvin. At 2000 degrees Kelvin, we have far surpassed any survivable temperatures with or without survival suit. While insanely hot, it will dwarf by the numbers yet to come. Lead melts at 2022 degrees. Silver boils at 2435 degrees. And the average surface temperature of an M-class star is about 3000 degrees Kelvin at its surface. Proxima Centauri, the nearest star to Earth after the Sun, has a surface temperature of 3042 degrees. The surface temperature of Barnard's star is 3134 degrees, which is also the boiling point for iron. Silicon boils away at 3538 degrees, and the red supergiant Betelgeuse has a surface temperature of 3590 degrees. Large stars drop their surface temperature because the area the heat has to cover is increased significantly by their size. The non-metal carbon melts at 3675 degrees Kelvin. Carbon is one of the most vital elements in the biochemistry, making up about 20% of any living organism's mass on average. Slightly above this, at 3678 degrees, the last solid element of tungsten is forced into liquid form. The surface temperature of the red giant Aldebaran is 3900 degrees. Carbon then boils at 4027 degrees above zero, and the average surface temperature of a K-class star is 4500 degrees Kelvin. The star, Epsilon Eridani, has a surface temperature of 5084 degrees. Epsilon Eridani is a star about 10 light years away from us, which is relatively young. Tau Ceti is another nearby solar analog star and has a surface temperature of 5344 degrees Kelvin. The average G-class star has a surface temperature around 5500 degrees. The surface of the Earth's core is estimated to be a good 5700 degrees. The surface temperature of the Sun rises to approximately 5778 degrees Kelvin. Our star is in fact slightly hotter than the surface of our planet's core. At 1503 degrees Kelvin, the last liquid element, the heavy metal of rhenium, at last boils away. We are now very far above any naturally familiar temperature. Every element has been forced into a gaseous state, yet we can go much higher still. At 6000 degrees is the temperature of the absolute core of our planet. It is also the mean temperature of our universe about 300,000 years after the Big Bang, and the surface temperature of Polaris, the northern pole star. At 6300 degrees is the average surface temperature of an F-class star. Procyon, the nearest F-class star, has a surface temperature slightly higher, at 6530. The average A-class star has a surface temperature of 7600 degrees Kelvin. At 7735 degrees, monoatomic ideal gas has 1 electron volt of kinetic energy. The star Fomalhaut clocks in at 8590, Vega at 9600, and Sirius at 9900 degrees. The Pistol star has a surface temperature of 11,800 degrees. Rigel has 12,000. And Regulus has 12,460, Algol at 13,000. The average surface temperature of a B-class star is 15,200 Kelvin. The mean temperature of the universe 10,000 years after the Big Bang was 25,000, as is the surface temperature on the white dwarf Sirius B. Mintaka and Alnitak are 29,500 degrees Kelvin, and the surface temperature of an average O-class star is 30,000 degrees. Eta Carina, one of the most volatile stars in the Milky Way, has a soaring surface temperature of 35,000 degrees, and the core of a protostar, which has yet to begin nuclear fusion, is estimated at 50,000 30,000 Kelvin. Regor has a surface temperature of 57,000 degrees Kelvin, and the central star, also known as the planetary nebula nucleus, or PNN, of the Cat's Eye Nebula, has an estimated surface temperature of 80,000 Kelvins. Regor is in the lower class of Wolf-Rayet stars. The average Wolf-Rayet star has a surface temperature of around 100,000 Kelvins. The PNN of the Ring Nebula clocks in at 125,000 degrees. At a temperature of 210 Kelvins, WR102 is the hottest star found. Degenerate stars, however, can far surpass this temperature. The Vela pulsar, for example, has a surface temperature of 280,000 kelvins. Pulsars are rapidly rotating neutron stars. 300,000 kelvins is the temperature you would experience about 17 meters from the atomic bomb dropped on Hiroshima in 1945. The PNN of the Spirograph Nebula clocks at a surface temperature of 422,000 kelvins. At 800,000 kelvins is the temperature of the average solar winds, and also the estimated surface temperature of the suspected quark star 3C58. The core of a threshold brown dwarf star can reach about 1 million degrees Kelvin. The Crab pulsar has a surface temperature of 1.6 million degrees, and the cores of red dwarfs reach 2.5 million. Orange dwarfs tend to reach 10 million in their core, and the Tsar Bomba, the largest nuclear weapon ever to be detonated, had a detonation temperature of over 11 million kelvins. Our sun itself has a core temperature of a soaring 15.6 million kelvins, an extremely hot temperature needed for its nuclear fusion. At these temperatures, gaseous matter is no longer stable. The electrons melt free from the atom, and the matter transits into plasma. However, we find again no limit in sight to the ever-increasing temperature here. The average F-class star has a core temperature of 20 million, followed by A-class at 30 million, B-class at 50 million, and finally O-class at 80 million. The average Wolf-Rayet stars reach 135 million kelvins in their core, and a newly formed white dwarf star has the core temperature between 500 million and 1 billion Kelvin. 1 billion Kelvin was the average temperature of the universe 100 seconds after the Big Bang. 10 billion Kelvin is the temperature achieved in an average supernova, and 1 second after the Big Bang. In the accretion disks of a quasar, temperatures reach about 700 billion kelvins, and in a newly formed neutron star, the core temperature rises to 1 trillion Kelvin. It's getting hot enough now to get matter to do some trippy stuff. Plasma itself melts into quark gluon plasma, where the protons and neutrons themselves have molten into their composite quarks. At 3.6 trillion Kelvin, matter doubles in mass due to relativistic effects, and around 4 trillion Kelvin, proton and antiproton reactions occur. 5.5 trillion Kelvin is the highest man-made temperature in thermal equilibrium for the Large Hadron Collider collisions. 100 microseconds after the Big Bang, the universe was still a hot 10 trillion kelvins, and the core temperature of a theoretical quark star is estimated at 20 to 25 trillion kelvins. When a hypernova releases a gamma ray burst, it generates a temperature of 67 trillion degrees Kelvin at 2.8 quadrillion. That is 2.8 petakelvins. Two of the four fundamental forces of our universe, the electromagnetic and the weak nuclear force, combine into the electroweak force. The higher the temperature rises, the more the forces move towards grand unification. At 2 quintillion, say exakelvins, is the temperature of heavy nuclear collisions at the LHC. Dark matter in an active galactic nucleus can reach to 1 sextillion, that is zeta kelvin, and 10 octillion kelvins, that's 10,000 yota kelvins. The strong nuclear force joins with the electroweak force, unifying into the electronuclear force. Then at 1 nonillion kelvins, 1 million yota kelvins, we reach the H-door temperature of strings. Normal matter is no longer stable and falls apart into energy. Then at 141.7 nonillion degrees, gravity joins in and the grand unification theory is realized. Current physics breaks down at or above this point because we currently lack a quantum theory of gravity. This is also the temperature 1 Planck time after the Big Bang happened. This temperature is known as the Planck temperature. Remember when at the Draper point objects start to glow a dim red? That's because the harder the object gets, the smaller the wavelength of the emitted light will be. When an object reaches a temperature of 141.7 nonillion kelvins, the radiation it would emit would have a wavelength of 1 Planck length, which according to quantum mechanics is the shortest distance possible. This is where we finally run into a wall. This Planck temperature sets a weirdly limit for temperature increase. Theoretically, you could still add more energy to the system, thus heating it further, but the wavelength would start to violate quantum mechanics. The point is that physics breaks down here. We don't know what would happen above this temperature. It's quite likely only a singularity would surpass this temperature, meaning a Kugelblitz would form, but other than that we only have speculation above this temperature. So I have to end this video a bit inconclusive about how hot it can truly get, but I hope I made you able to grasp the immense scale of temperatures. This has been EG Science, and thank you for watching.